All right, everyone. So we are going to study today about internal energy, thereafter Zeroth Law of Thermodynamics, thereafter the first law of thermodynamics, and at last we will be studying about enthalpy. So let's start with what is an internal energy. So let us consider a system to understand it better. Suppose I have taken an example of a liquid. You can simply extend this idea in the other system as well. In the liquid particle, you know that one molecule is attracting other molecule and they are translating also, and if suppose molecule is diatomic or polyatomic, if suppose it is H2O, then it is having a rotational motion as well, right? So then what is internal energy? So internal energy is the sum of the all type of internal potential energy and internal kinetic energy. So when I talk about kinetic energy, internal kinetic energy, so you may ask a question, sir, what kind of internal kinetic energy? So my dear, vibrational kinetic energy associated with translational motion, kinetic energy associated with rotational motion, all type of this will be taken into it. Now you may ask, sir, if we look at even deeper into it, like we have the case of atom, the electrons are also in motion around the nucleus. So are we supposed to consider that also? Yes. Anything with which a system is made up of even the tiniest possible particle, we are supposed to look all of these things. So what about, sir, if a body like this as a whole is moving with a speed, which type of energy is this? So it is an external energy. Now it is not the part of internal energy. Internal energy means within the system, if you are suppose here and observing the motion of the particle with which that particular system is made up of, that is considered to be internal energy. All right. So what is an internal energy? Sum of all type of internal potential and internal kinetic energy. Sum of all type of internal potential and internal kinetic energy. Next thing, very very important about it, can we calculate this? The absolute value, can we calculate? So you can think by yourself only, can you calculate the kinetic energy of an electron, which is the part of the molecule, which is the part of the atom? You can't calculate, right? Because for hydrogen atom we do have one formula, but that is also not valid. So kinetic energy we can't calculate for the electron nucleus system. Now you imagine if we are not having any governing formula of the force which are operating out there, so how can we get that? So there is no meaning of talking about the internal energy, and like that also you can think that the potential energy is also something which we can't actually calculate. So absolute value, we cannot calculate the absolute value. We can't calculate the absolute value. We can't calculate the absolute value of internal energy. Right? Next very important point associated with that is, I told you that work, heat capacities, these are path function, whereas internal energy, enthalpy, Gibbs free energy, entropy, these are state functions. So internal energy is a state function. It is a state function. So the moment I say state function means, suppose in a process you are at initial state A and at B, and you are adopting different pathways. You are reaching here, then you are reaching like this, then you are reaching like this, right? So if the state 1 and 2 is fixed, so my dear, the value of delta u1 must be equal to delta u2 must be equal to delta u3, means delta u1 will be equal to delta u2 will be equal to delta u3. Okay, w might be different because it is a path function, that may or may not be equal. So w1 might not be equal to w2, might not be equal to w3, heat might not be equal to, but this is very certain because it is a state function and initial and final state are fixed. No matter which path you are adopting, this value will be fixed for it. That's what the meaning of state function is. We are going to use this specific property in a very nice way, right? So internal energy is the sum of all internal potential energy and internal kinetic energy, and we cannot calculate the absolute value, and this is how we are relating it. Now the question is, if we cannot calculate the value of absolute value, then it is meaningless. Don't you think that it is meaningless to discuss about this? Answer is no. Even if we can't calculate it, but we can measure in terms of heat. How? For that we have to understand the first law of thermodynamics. And before covering the first law of thermodynamics, I want to discuss a little bit about zeroth law of thermodynamics, right? So let's talk about zeroth law of thermodynamics first. Alright, so what is zeroth law of thermodynamics? Let us consider three bodies, body A, body B and body C. So now what is the meaning of zeroth law of thermodynamics? It is related with the thermal equilibrium basically. This law is related with the thermal equilibrium, right? So suppose body A and B are in thermal equilibrium. And body B is in equilibrium, in thermal equilibrium with C. So two bodies are in thermal equilibrium. The third body is in thermal equilibrium with one of them. So don't you think that all of three will have the same temperature? Means they must all be in thermal equilibrium. That's what the statement actually means. Okay. So zeroth law of thermodynamics states that if two thermodynamic systems are each in equilibrium with a third one, if two thermodynamic systems are each in thermal equilibrium with third one. Then they are in thermal equilibrium with each other. Let us once again understand the meaning of this. Let us once again understand the meaning of this. That these three bodies are there. If suppose B is in equilibrium with A and B is in equilibrium with C, means AB are in equilibrium and BC are in equilibrium, thermal equilibrium I mean to say. In that case, all three of them are in thermal equilibrium, means the temperature of these three systems must be same. This is how we state zeroth law. I hope you would have got the clarity into it. Zeroth law. Okay, this is related with that one. Now let's talk about the first law of thermodynamics. Now what is it? What is the first law of thermodynamics? So now for understanding it, let us take a system and then accordingly think that. Suppose for simplicity I am taking a system of an ideal gas. Right, and this is the external agent. You can say that external agent is there, which is responsible for compressing or expanding this, right, depending on the pressure. Now you tell me what will happen if I am supplying heat from outside and at the same time the external agent is performing work also, means trying to compress it. So what will happen essentially to the system? Now there are two pathways with which it is consuming energy, Q and W, and don't you think that they are going to increase the internal energy of the system? Because where else this energy can go? If you are supplying heat, if you are performing work on this, because we know that the energy can neither be created nor be destroyed, so it will change from one form to other. So if I have supplied heat and work, then these will definitely change its internal energy. That's what the only parameter left. So yes, this is indirectly, or you can say directly also, the law of energy conservation. Okay, so please make a note. The first law of thermodynamics is a version of the law of conservation of energy. Means energy can neither be created nor be destroyed. It can only be transformed from one form to other. Right? So this is relating the work and heat with internal energy. So how can we write? Work done by external agent plus the heat supplied by external agent is going to change the internal energy. Or popularly we can write Q is equal to delta U minus W. This is how we used to write. Now you remember I told you that we cannot measure U2, we cannot measure U1, but still we can get U2 minus U1, basically change in internal energy. How? How can we get? So you do some specific changes, you may get that. What? You know, heat is a measurable quantity. With the calorimeter, we can measure how much heat is transferred. Like suppose if we are having a sample of water which is at, say for example, 10 degrees centigrade, if Q amount of heat is transferred to it and we got that its temperature raised to 50 degrees centigrade and mass is given to us. So can't you calculate heat? Q will be equal to m into S into delta T. Alright. So Q is a measurable form of energy. So if anyhow we are ensuring that the work done is 0, in that case with that particular method we can get the value of delta U. So how to ensure that work is 0? And we know that W is nothing but minus integral of P dV. So if volume becomes constant, if V is constant, don't you think W will be 0? So yes, that's what the statement is. Means at constant volume, heat exchanged will be equal to change in internal energy. That's a very important statement I am telling to you. So at constant volume, heat exchange is equal to change in internal energy. That is, delta U is nothing but Q at constant volume, constant volume. Whenever we are writing like this, it means at constant volume. So yes, so you measure the heat supplied by keeping the volume of the system fixed, means make it rigid and then just measure. So that will be the, whatever the heat you are supplying, that will be the change in internal energy. Okay. All right. Now suppose if the system is ideal gas, in that case can we write heat for ideal gas? Can we write N into Cv into delta T? Yes or no? How can I write that? Because we know that Q at constant volume, means isochoric process, then this will be molar heat capacity at constant volume, means Cv. So Qv is equal to this, and this is nothing but delta U. Right. So for ideal gas we have this thing, this relation you can. So this relation tells that if the temperature gap is not there, then in that case there will not be any change in internal energy, right? So very specific, QV is equal to this and this is equal to delta U, very very important. Otherwise this QV we cannot write like this for any liquid. Say for example you are considering H2O liquid transforming into H2O vapor. Can we apply this? No, this is a phase transfer, and in phase transfer we cannot apply this equation. This is not valid now, but this is valid. Heat supplied, if the volume is constant, we can get this value. So we will look at the other way by how to calculate this particular thing. We will look at the other ways. But anyway, till now, heat supplied at constant volume is equal to change in internal energy. That's how we used to measure. Okay. Now, as I told you that this delta U, in fact U is a state function, right? As I told you that internal energy over here is a state function. So suppose, my dear, if there are 3 pathways between point A to B, there are 3 different pathways by which it is going on. The system is changed from its initial state to final state. In that case, if suppose by path 1, if Q1 is given as 200 and W is given as, say for example 200, and between the same state A and B the things are going on, and in the second case suppose W is 100, Q is question mark, in third case suppose Q is 50 and W is question mark, then how to get that? So this is what the application of the first law is. Between state A to B, one thing is very clear, that whether you are going by first or by second or by third, delta U must be constant. And we have got delta U1 for the first process. These two values are given to us, that is Q1 plus W1. How much it is given? 200 plus 200, which means 400 is given to us. So suppose if they are given in calorie, then this is given as 4 calorie. Now in the second case also this value will be same. So by using the second, for second we can say that delta U2 is given to us as 400, and that will be equal to W2 plus Q2. And what is W2 this time? 100 is given, Q we don't know. So Q2 will be how much? 300 calorie. And like that you can apply it here. This is very wonderful application of the first law of thermodynamics, because U is a state function. So fine everyone, so I would like to stop here only. In the next video lecture I will explain about the enthalpy internal energy relation and how can we measure the enthalpy in the form of heat. Okay, so that's all for the class now.